Hello. The purpose of this presentation is to give a detailed view on the objective function used in the paper entitled as Colorization using Optimization, and also talk about the original implementation of the authors. So before diving into the objective function, let us have a quick recap on some important information regarding this algorithm. First one is the color space. So in this paper, YUV color space have been used. Y channel is the monochromatic luminance channel or the grayscale channel, which is defined as the intensity channel in this paper, and U and V are the chrominance channels or the color channels. So input of this algorithm is an intensity image or a grayscale image which has some color scribbles given by the user, which will act as color hints, and outputs are two color images U and V. Now R and S, these two notation have been used to denote pixel positions, where R denotes position of a particular pixel and S denotes the neighboring pixel of that particular pixel. Now to have a view of what this R and S means is let us imagine one 9 by 9 pixel grid, and if we talk about the center pixel, that is R, and if we talk about the surrounding 8 pixels, these are S. So if we say YR, that means we are talking about intensity or grayscale value or the luminance value of R pixel. And the main objective of this algorithm is, as we already know, is if two neighboring pixels have similar intensities, they should have similar colors. Now the algorithm is the user will give some color hints on a grayscale, and the color has to be propagated, and to have similar colors between two pixels, they should have similar intensity values. So the objective function of this algorithm is to minimize the difference between color UR pixel at R and the weighted average of the colors at neighboring pixels. In simpler words, let us see the equation here. So JU, it means we are optimizing for U channel, and the V channel will be the same. So we have to optimize for two channels, U channel and V channel. So we can see here that summation of R for UR, which means R pixel at U channel, for all R pixels, we have to minimize the intensity of US, the neighboring pixels, and the US is the weighted average of the colors. So weighted average, which means that R pixel will have some relationship with all neighboring pixels, and this relationship function or the affinity function is defined as a function of the mean of the neighboring pixels and the variance of the neighboring pixels. So which means so R at Y channel minus the mean of all neighboring pixels, which means we are minimizing the intensity values of the neighboring pixels here. And also if we can see YS, which means we have to minimize the intensity of the neighboring pixels, and it's divided by or normalized by the variance, so that we have like less variance and we have minimum mean or minimum average, weighted average of the neighboring pixel. So in simpler terms, each pixel will calculate the difference between its own intensity value and the weighted average of the intensities of the neighboring pixels. Now this affinity function is the most important function in this paper, because this is the optimization problem, the objective function of the optimization problem, and this is the constraint of that optimization problem. And we can see from the equation that this objective function is a quadratic in nature, and the relationship among the pixels and the neighboring pixels are linear here. There are no non-linear activities, so we can solve it by simply putting them in matrix form. So the original implementation by the authors is BI. In our case, BI denotes a pixel whose color has been defined by user. So recall that we have a grayscale image and user will give some color hints or color scribbles. So some pixels will have color information and most of the pixels will have grayscale or gray value or just luminance value or black and white values. So those colors given by the users will have to be propagated to the grayscale images. Now how do they propagate? We will calculate the intensity value. So if two pixels have similar intensities, they should have similar colors. So if we're talking about u pixel r, if we go to equation here, u pixel r, suppose this one has color information, this neighboring pixel does not have color information, but their intensities are same. So this value should be given to all of the neighboring pixels because the intensities are same. Now because the cost function is quadratic and the constraint was linear, the authors tried the sparse system of linear equation method or the matrix method to solve the equation for each pixel. I will talk about this in the next slides. So they have implemented pseudo inverse method, and we can see here there is a matrix called D. D is actually a diagonal matrix whose diagonal elements are the sum of the affinities. So sum of the affinities means like the sum of all relationship with a pixel and its surrounding pixel. And if we see this whole implementation in matrix view, we will have something like this. As we can see that this is a diagonal matrix and only the diagonal values are non-zero, everything else is zero here. So we can see that this WRS1 is based on the affinity function here. The affinity function, as we can see, the affinity function is defined as the relationship between one pixel and its surrounding pixels. So we can see the whole matrix here, which has the affinity values of for all pixels. That's why this is an m into m matrix denoting affinity, and this vector here denotes all the pixels. So x1 means 0th pixel, x2 means the first pixel, x3 means second pixel. So we have to solve this equation for each pixel, and this vector here is the resultant pixel having the optimized value. So in the original implementation, the optimization was done through matrix multiplication. So if we do matrix multiplication with this row with this column, as all the values here are zeros, we will have only this value, which means that affinity values multiplied by the pixel values, we are solving for one pixel, and affinity value 2 with pixel value 2, we are solving for pixel 2. So for each multiplication we will get the optimized pixel values, which will have the similar colors, because the affinity function calculates the intensity values of difference of intensity values of one center pixel and its surrounding pixels. Now we have to take note of one notation here, that is user input, so B0. So based on the affinity we are finding the values of each pixel. But what happens if we have a color value specified by the user input? In that case we don't actually calculate the affinity, because affinity serves as the basis for the color values. So we use affinity function to find the color values of a pixel, but in case of user input we already have that color information. In that case the affinity will be 0. So to recap the whole process, the affinities or the relationship matrix is given as a diagonal matrix where all the values are 0 except for the diagonal matrix, and all the diagonal matrix contains relationship with a center pixel and its surrounding pixels. And this matrix, this very sparse matrix, is multiplied with the pixels so that we can have the optimized output pixels or optimized pixel values. So this whole process is done for U channel and then V channel, and for the final result we concatenate, or we add U, Y, U, V, 3 channels to have the colorized image. So that is the original implementation of the authors, as well as the explanation for the objective function used here. So to have a simple recap, we have to minimize the intensity value or the luminance value of one pixel and its surrounding pixels so that they can have same color based on the affinity function. I think that sums up the objective function of this paper. Please let me know if you have any question. Thank you for listening to this presentation.